Oh, right. So let me put that on. That didn't go up over there. Let's see. Okay, there it is. So basically, when you can only expand the octet when you have atomic orbitals that are available to put that electron density into it. And so things that expand their octets, it starts in the 3 shell. So in other words, where we have sodium, magnesium, aluminum, silicon, phosphorus, phosphorus and sulfur are atoms that can typically expand their octet. The reason why is they have access energetically to the 3 shell, which allows them to dump electron density into d orbital type areas. Does that make sense? So anything above that can't expand the octet. If anything, there are violations of less than an octet. Remember, boron is one of those few atoms that you can form 3 bonds and have 6 electrons around it, and it's stable. We'll talk about boron again. Okay. How about the second one? I was kind of mulling this one around in my head. So why can't that second molecule exist? And I came up with something that looked like this as just one path. So if I have carbon, nitrogen, I have 6 hydrogens to put around it. I'm looking to fill up octets. So in other words, 1, 2, 3, 4, 5, 6. Okay. I could maybe even do something like this. And if you were to count let's make sure this one's right. 2 carbons, 6 hydrogens, 2 carbons, 1, 2, 3, 5, 6 hydrogens. Everything works. I put my lone pairs in. So why can't that molecule exist the way it's written? What am I missing on these structures that is really causing me a problem here? Yeah.
Does nitrogen not have enough bonds?
I'm sorry, what was that?
Does nitrogen not have enough bonds?
Oh, to this one? We could probably get away with it, but I love where you're going with it. It doesn't have another bond to it, but what does that mean? Yeah.
Carbon, you can't make a double bond with it because carbon's already full.
Can't make a double bond to this because carbon's already full. Love that too, right? So I can't form a double bond here because that would violate the octet on carbon. I agree, but that's not the reason why. I love all these, yeah.
Well, the formula we're given on B doesn't have a charge in both of those ways.
There it is, right? What's wrong with this? If I count up the formal, if the formal charges around each one of these atoms, these are neutral. I'm cool with that. But when I get to here, I cannot draw a structure that doesn't have a charge. And that formula has no charge, which means that it can't exist. So in this case here, what would be the formal charge? And we're going to talk about this right away in the chapter 2 slides, in case this is a little bit rusty for you. But in this case here, if I had a single bond, each bond, because there's 2 electrons in it, I count 1 electron when I'm counting formal charges. That means I have 1, 2, 3, 4, 5, 6 electrons around nitrogen. If I count the number of valence electrons, it has to have 5 for neutral, which means I have 1 more than I need, which means that this would have an overall negative charge there. How about that one? How about that nitrogen? What would be the charge on there? Plus. Where does that come from? It has 1, 2, 3, 4 electrons around it. 5 is neutral. It's 1 less than neutral, which means that that would be a positive charge. So the reason why that question, I think, is a good one to lead out with is it really does ping the ability to draw these Lewis structures and what are the consequences of having these different arrangement of atoms in space. And of course, the insta way to get a problem wrong is to draw 5 bonds to carbon. Unfortunately, some of you will do it, and I will write very animated responses back to you. Yeah. Let's see, on this one here, let's see. I think because I use the lone pair to form that extra nitrogen hydrogen bond, I don't need to have a lone pair on it. But I used it to form the bond with hydrogen. mull it over. Okay, cool. Okay, how about a question like this? A real hit and run type question for this unit. So, what kind of hybridization would you expect for the carbon atom, for each carbon atom in the molecule? And I'm going to be a little bit more specific so we're not just walking through it. I'm going to use this cursor, and I'm going to ask you if is it sp3, sp2, or sp? Let's go with that carbon right there. sp3, I agree, right? 4 different things around it. It's going to have a tetrahedral geometry. How about that nitrogen right there? Okay, I'm liking it, right? Starting to build up. We're a little cold. How about that carbon right there? Ooh, I think you guys are getting it, right? So what are you triggering off of? You're looking at, I have 3 electron-containing things around that atom. The double bond's also a dead giveaway too, because you have to have an unhybridized p orbital in order to form double bonds, which means it can't be sp3, sp2, or sp. How about that carbon right there?
sp3.
Ooh, I heard a mix there. How many different things are around that carbon atom? Let me get my cursor out of the way.
3, 4.
Aren't there 4 things around it? I have 2 hydrogens. I have a carbon here. I have an OH there. That makes 4 things around it, which makes that sp3. I'm looking for a generic, yeah. Yes, when you have carbanions, you can have lone pairs on a carbon. Makes a really wicked base, which we'll talk about. Yeah.
How do you know that the O would also be around the carbon if it's not directly?
This thing right here? Okay, got it. Yeah, so when you're looking at these line structures where you get these hybrid condensed formulas, with that CH2, when I'm drawing something like that, and I believe that's how they have it written, what that's really describing is the fact, for me to get an octet around that molecule and not have a residual formal charge, it'd be carbon.
So the dead get away. All I want you to look at is the
Right,
mod.
so in these structures,
So one
that's an alcohol
SP
functional group, those things will stay together.
2 lines?
Yeah. Yeah.
It's the
Yeah.
bonds are the dead
On one of the
get away.
homework questions,
Don't
we
think
had
about too
to
much
like
about it.
count, or like
Because he
write,
said one of
a
these guys
formula
was
based
like
on the number of hydrogens and oxygens.
SP3.
And I was a little bit confused because in class we had talked about that if there's an
Right.
alcohol
Did you
group,
say this
always
was
leave it
SP3?
as an alcohol
Yes.
group. But it wanted it like lumped in with the other one. On
Right.
a test or quiz, would we always have to leave the alcohol separate?
Right, so depends the type of question. I love the question. So in this type of question here, where I'm talking about structure, I'm keeping the OH together. If I'm saying write a molecular formula to me, then that is a generic counting of all the atoms that are there, which means you break everything apart. Hydrogens go with hydrogens, oxygen go with oxygen. Okay. Actually, before I draw it up here, let me just see. What is the bond angle between that carbon, and that oxygen? Doesn't have to be exact.
109.
I'm gonna close my eyes. Wait, say it again.
109.
109. Where's that 109 coming from?
sp3.
From the hybridization, right?
What I wanted to say was like, so, what do you have 19 electrons of that structure, but only 5?
You talking about this one here? Okay. Okay, so, yeah, well, I'll finish that thought and then I'll go back to this one. Yeah, okay. So you triggered off of the fact that this was an sp3 hybridized center because it has 4 different things around it. sp3 hybridized centers and generically have 109 degrees bonding. Right, so that's a different way in which I can ask you a hybridization question. And then before I get to William's question, let's just do this one here. What is the bond angle between carbon, nitrogen, carbon here?
120.
Wait, say it again.
120.
120, and it's 120 because it's sp2 hybridized. Right, so why is that sp2 hybridized? There's a lone pair of electrons, of course, to complete that octet on nitrogen. That's the third containing thing, which makes it sp2, which makes the bond angle 120. Okay, let's go back here. Alright, so in this case here, we have 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12, 14, 16 electrons. This one here has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. I was drawing a generic structure here for that formula, so I wasn't being beholden to how many lone pairs of electrons were there. Is that kind of where the communication's going? Yeah, so in that particular problem, because of how it was written, I got away with not worrying about the fact that these two had two different sets of valence electrons because I was just trying to match the formula. Yeah, but I still think that positive charge is right. Do we agree? On that nitrogen?
We can't put it away, it's just
No, in this case here, I counted for that lone pair going, because if I hadn't drawn this, so nitrogen, carbon, carbon, and I put a hydrogen here, just one, then I would agree there should be a lone pair on there. We'll talk about that.
Yeah, we can talk about it.
Yeah, okay, sounds good. Yeah. Okay. I feel like that one went okay. And we'll end with this one, and then we'll get into chapter 2, where we talk about formal charges. And so the most stable organic species is a tetravalent carbon, period. That's understatement of the century. But species that are trivalent carbons also exist. These carbocations that you guys will learn to love in this course exist. They result in all sorts of interesting rearrangement chemistry. And so this question just deals with the methyl carbocation. So there's the structure of it. C, H, 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 positive. Doesn't have 8 electrons, right? Doesn't have an octet around it. However, this is a perfectly stable species. And it gets more and more stable the more and more things contribute to the stabilizing the positive charge. So how many valence electrons does the positively charged carbon atom have? How many valence electrons did it have? 3, right? So I'm forming 3 bonds. That means it has 3 valence electrons at that point to form those 3 bonds. Okay? What hybridization do you expect from this carbon? sp3, sp2, or sp? Yeah, behind you. Yeah, go ahead.
Would it be SP3?
You're just going to the generic, how many electron-containing things are around that carbon atom?
SP2.
sp2, right? Because I have 3 different things around it, that atom is actually sp2 hybridized. Okay. What geometry would that carbocation have then? Trigonal planar. Be as flat as a board, which allows you to react from either the top or the bottom, which we'll see when we get into nucleophilic additions into that. So this would be trigonal planar, just like any other sp2 hybridized set that we would talk about. Okay, so I'm going to leave it there for chapter 1. You'll notice in the end of the chapter 1 slides, I put a whole bunch of end of the chapter problems in addition to the homework that you just did, in case you want extra practice. And I hope you're seeing how, by thinking of geometries with by thinking of a geometry with reference to how many different electron-containing things are there, that rule never fails. It never fails, as long as you can count to 4. Right? I have 4 things there, I have 3 things there, I have 2 things there. That consequence is a result of the hybrid orbitals that we create. Yeah, go ahead.
What if the carbon has 2 pairs, like lone pairs?
2 lone pairs, that makes a carbon.
One lone pair of electrons. Like instead of positive, it will be negative.
Right. Okay, yeah, I like it. Okay, let's get into it. So let's see. So I'm going to draw that methyl with 2 lone pairs. With 3 bonds to it. So in other words, I'm going to put a lone pair on it, and I'm going to put the hydrogens around it. Am I missing something? a negative charge, right? Now, why do I know it's a negative charge? If I count the formal charge here, it's 1, 2, 3, 4, 5. That's one more than carbon needs, so this is a methyl anion. What's the hybridization of this methyl anion? sp3. Why is it sp3? 1, 2, 3, 4. Why am I drawing this not flat? I'm drawing it as if it was pyramidal. Because it's in the form of a tetrahedron and I just removed one of the pieces. Almost bored. That's where I want you guys to be. Not a problem. Okay. Onward we go. So now we're in chapter 2, and of course quiz 1 that you guys will take covers both chapters 1 and 2, and that quiz takes place next Thursday, so it's coming relatively quickly. What we're going to talk about is polar covalent bonds, formal charges. We'll even get into resonance a little bit if we have time. And so just as I started off the class, a covalent bond is the sharing of electrons between two atoms that generates a stable interaction, the storage of energy. In organic structures, this electron sharing is biased based on the atoms that are part of that structure. The more or the greater the difference of the electronegativity of two atoms, the more that cloud, that electron cloud that's negatively charged, gets geared towards the more electronegative atoms. It shifts where the electrons are at. So in this case here, when we have just a covalent bond between two atoms that are identical, neither wins. It's equal sharing. So if I was to describe the bonding in the hydrogen atom, the electrons are shared equally between those two atoms. There's no polarity to that molecule. That molecule would be considered non-polar. There is no bias. However, if you now create, in this case here, I'm just going to draw generically an alcohol group, and if I was to describe the bonding between these two atoms, this atom, or the OH, the oxygen is going to bias that bond. It's going to create a polar covalent bond. I can draw this with reference to the electron cloud this way. Kind of artsy-fartsy, but it's getting my point. Where I'm saying here, if this is the electron density shared between that bond, then the electron density is going to reside more towards the oxygen, and as a result, it polarizes that bond, creating something called a polar covalent bond. Bonding electrons are attracted more strongly by one atom rather than the other. And if that electronegativity difference gets so large, they don't want to share anymore. And then you end up getting positively charged and negatively charged species as a result of that. And this describes the differences, the ionic character of these bonds. What is the ionic character? Ionic character comes from the fact that when you look at this periodic table, and of course this is the showing the highest electronegative atom, which is fluorine, of course, and everything that emanates away from it, the electronegativity goes down as you go away from fluorine. So in other words, as you go this way, you can even see it in the numbers. This is a 4, and as you go this way, that's a 0.7. And that has to deal with shielding and all this other wonderful stuff you learned in Gen Chem. But at the end of the day, this table also tells you what bonds are going to be more ionic-like and less ionic-like, which are going to be more polar or less polar. And of course, these differences in electronegativity produce the bond polarity that you're seeing. The bigger the difference, the more polarized the bond's going to be. Metals on the left side of the periodic table, of course, attract electrons weakly. Why is that? Well, it's because sodium is always a +1 ion, because if it loses one electron from the valence shell, it becomes a positively charged sodium, and it has a noble gas core configuration, which is the most stable electron configuration. Of course, that would make these atoms the least electronegative atoms on the periodic table, because they don't want electrons. Electronegativity means that the electron wants to be there. The atom wants to hold that electron density. It doesn't want to give it up. Metal ions end up doing that. On the exact opposite side, halogens end up being some of the most electronegative atoms, meaning that they're always polarizing bonds and dragging electron density towards them. So then there's these generic rules about if the difference in electronegativity is less than 2, it's considered a polar covalent bond. If it's greater than 2, it ends up being ionic bonds. It's a blur, okay? And because it's a blur, I would have a very difficult time wanting to test this directly because it's not true half the time. Meaning that you can have something like, for example, methyl lithium. Let's see, so methyl lithium. So what am I drawing here? I'm drawing methyl minus and lithium plus as a compound. And the reason why I'm using that example is that carbon has a relatively moderately high electronegativity and lithium does not. Meaning the difference in that molecule, and I think I even have it on the next slide, which is right here. This is methyl lithium. This is showing the electron cloud where you have red. That means the electrons are being localized there. Where you have blue, it means that the electrons are not there. This is showing a map of the electrostatic potential of this molecule, how polarized that molecule is going to be. So when they show methyl lithium here down the lower right-hand corner, the difference there is a 1.5. So by any stretch of the mind, you would say, hey, that's a polar covalent bond. It certainly doesn't behave like it. Methyl lithium is probably one of the most rip-roaring bases we can have. The reason why is methyl minus is what is generated there, not a methyl lithium species. Yeah, go ahead.
So like on our quizzes and tests, are we not going to gauge like that exactly? Like you're not going to ask us a question?
No, I'm a little bit more spiritual with this part of the class. So in other words, when I talk about this, what I'm really just wanting you to have in your mind set is the fact that fluorine is the most electronegative atom. Electronegativity decreases as you go away from it. And that the farther away the two atoms get in that periodic table, the more likely it is that the more polar that bond will be. Okay.
So it's just pure trans.
Okay. Okay, so in this case here, we're describing methyl lithium like this, and really what the book is wanting us to do is for me to actually render methyl lithium to you like that. Right? It's saying it has an electronegativity difference of 1.5. That would be a polar covalent bond. They're saying it's covalent. So if it's covalent, then this would be the perfect rendering of methyl lithium. This would be incorrect. I just can't live in a world where that's incorrect. So in other words, when we get into really polarized bonds, there are certain times where the electrode sharing is so different that you get ionic species. Other times, the atoms find stability in sharing. Both of these would be correct in my mind, and they're correct for probably everybody from McMurray. So, who wrote the book, by the way? So what are we talking about here? We're talking about how electrons are being shifted, how they're being shared, and this can be described as something called the inductive effect, induction. Induction, that is the pushing and pulling of electrons, in this case, between two atoms. Shifting of electrons in a sigma bond in response to electronegativity of nearby atoms. So what I'm describing is this. The oxygen is inducing a response. It's inductively pulling those electrons from the hydrogen through that single bond. And we're going to see this all the time in this class, where most of the effects we see in carbon structures are inductive, meaning certain groups push electron density in, other groups take electron density out based on their electronegativities, and that leads to your chemical intuition, which is what we're slowly building here at the beginning. Why are things happening? Okay. And I think that this is a nice example here where we talk about methyl lithium, where this is a very polarized bond. But however, in methane, what do we see? We don't see reds and blues. We see green, which is the color of apathy in electrons in electrostatic maps, meaning that there's no bias there. The electrons are equally distributed around that molecule, and as a result, you would describe each bond in methane and I think this is where it gets a little bit muddled in Gen Chem. I would describe this carbon-hydrogen bond as a polar covalent bond. That we agree, right? But this molecule is if I spell that right, non-polar. So the bonds within the molecule are polar, covalent, but yet the molecule itself is non-polar. You guys remember why that happens? Right? All the different bonds in that molecule are all pointed at their inductive effects are all pointed directly opposite to each other, and as a result, there's no net residual dipole of this molecule. However, if I was to take this, let's see, H, and now do O, H, what have I done? I've created a bias in this molecule. I've created a region in which the electrons are no longer being shared equally. I've created a polar moment here. So in this case, I would say that the dipole of this molecule would be directed towards that carbon-oxygen bond. The reason why is that those two atoms are not sharing the electron density equally compared to how the carbon-hydrogen bonds are inductively affecting it. So in other words, if I drew all the dipoles of this molecule, this dipole is pointed towards there. This is the molecular dipole. But then each one of these bonds, hydrogen bonds or carbon-hydrogen bonds, hydrogens inductively push electrons in. So what do I have? I have these electrons being pushed in from the hydrogens. I have the oxygen pulling electron density up, and that creates an overall molecular dipole moment towards that oxygen area, which makes it a polar molecule, and we'll talk more about that in just a second. So, familiar? Okay. Polar covalent bonds. So molecules are often polar based on the vector summation of the individual bond polarities and the lone pairs. That's exactly what this model is telling us, is the summation of all the individual bond polarities and the overall, which creates the overall molecular dipole of this molecule. That's true for every covalent molecule we'll deal with. And of course, like dissolves like. Polar compounds dissolve in polar solvents. Non-polar compounds dissolve in non-polar solvents, just like what you learned. And of course, these dipoles are measured in something called, Debye, which down at the bottom, sometimes you'll see this rendered as mu, and then a big D on the end of it, and that stands for Debye. And Debye, when you break out the units, are actually units of coulombs, which is units of charge, and meters, meaning distance of charge. So meters times the charge, the distances those charges are separated. Why this interest in charge? Well, because I'm biasing this molecule. I'm shifting electron density. This oxygen has more electron density than here, being dragged from it. So as a result, those are two charges being generated as a result of that. And that's the reason why molecular dipoles are measured in units of Debye, which are units of charge versus distance. Okay, so magnitudes of dipoles, the bigger that number gets, the more polar the molecule is, because you're getting large biases in the molecule. So here are three different ones that have moderately large dipole moments. So you have water on the left, 1.8 Debye, methanol on the right, 1.7, and of course ammonia, 1.47. Why do you think the dipole moment of methanol is less than that of water?
Because the H is carbon is about
I'm sorry, what was that?
the CH3 portion of the methanol.
Oh, yeah, I like where you're going with that. So in other words, why would water be more polar than something like methanol? The reason why is the CH3 component of it. The CH3 component would be non-polar, meaning you have carbon-hydrogen bonds that don't have large electronegativities. And so as a result, that methanol, so let me describe this a little bit more clearly. So why is methanol not as polar as water? I'm even biasing it a little bit to make them look the same. So in other words, here I have water, here I have methanol. If I was to draw the molecular dipole direction for this molecule, I would draw it like this. I have two lone pairs in tetrahedral space next to each other, and then I have two hydrogens pushing into them. This one here, what do we have? We have now a molecular dipole that looks something like this, but really where the difference comes is what's happening with that methyl group. It's not as polar as a hydrogen all by itself connected to an oxygen, meaning that there's certain bond polarities here that the electronegative difference between carbon and oxygen is not as great as that of hydrogen and oxygen. As a result, you don't get as much of a polarity, as a difference in the polarity. Structure function relationships, that's throughout this course. That's sort of the beginning of that discussion of, look, there are reasons why those numbers are the way they are, and it comes from the structure. Okay, so here's a table of a wide variety of dipole moments of some generic compounds, some of which you've seen before. For example, sodium chloride. None of you would describe that as a covalent compound. That would be an ionic compound. And as a result, they describe the dipole moment of sodium chloride as 9. I don't know how the hell they got that number. But in general, what they're trying to describe there is that the polarity of that ionic bond is far greater than 2. So that makes sense. When we get to now, we go from methanol to, we go from water to methanol to now carboxylic acid to then these thiols, we start to see now these differences, these sort of subtle differences in the structures. And all of these dipole changes are coming from the differences in electronegativities are getting less and less and less. And as a result, the dipole moments are getting smaller and smaller and smaller. And of course, if we have molecules that have some sort of equal symmetry, those molecules are considered, even though they have polar covalent bonds, they are considered non-polar compounds. So for example, CO2. I think that's even on the next slide. Yeah. So the absence of dipole moments occurs when you have two atoms in space that are equally contributing to those polar covalent bonds. So in the case of CO2, you would describe that bonding as carbon, CO. Where if I drew the dipole moments of each one of those CO bonds, they would be directly across from each other. They have a geometry of 180 degrees. As a result of that, there is no bias in that molecule for creating an overall molecular dipole, and as a result, that's a nonpolar molecule. Go.
So the more polar the molecule, the higher the dipole moment's going to be?
Right. The larger the molecular dipole, the bigger the dipole moment. Those dipole moments, just like what we're describing right here, this would be a relatively polar bond. Carbon and oxygens have relatively high differences in electronegativities. But because of the orientation in space, this molecule ends up having a mu of 0, meaning it has no dipole moment. Same thing happens for methane. Same thing happens for ethane, which is the reason why ethane and most alkanes are nonpolar. They have no molecular dipole moment. And in this case here, for the last one, benzene, which Rick Murray loves to use all throughout this course, and we'll talk about residence hybrids in just a minute. That would be the line structure of benzene. Every one of these atoms is sp2 hybridized, which means that this molecule is flat. Every one of these CH bonds are pointed directly across from each other and they're exactly the same, which means that that benzene with hydrogens there, that's a non-polar molecule. However, if I was to stick polar groups onto benzene, now I have polar molecules. So in this case here, benzene would have a dipole moment of 0, but if I was to create phenol, which means I replace a hydrogen with an OH, put an alcohol group on there, which would also be polar, dipole moment goes up to 1.38. If I put a methyl on there, it's 0.38. Huh. So I have phenol. And I have toluene, which is the second molecule here. You don't have to name organic, you don't have to name aromatic compounds in 313, that's saved for first thing in 314. But what we're talking about here is definitely a 313 subject. So these two molecules, this one here has a mu of 1.38, this one here has a mu of 0.38. Why is that happening? Even better, let's put the molecular dipoles on here. So if I draw an arrow like this with a positive there, I'm describing the fact that the electron density is being biased in this direction and I'm getting a delta positive in that direction, meaning I'm pulling electron density away. So if I drew the dipole moment for this bond here, I would draw something like that, wouldn't I? Wouldn't I? How about this methyl? That's a carbon atom there, right? That's a carbon atom there. Not a big difference in the polarities, wouldn't you say? Well, let's see. So how would I describe this? Well, these hydrogens, I know I've described the inductive effect of these hydrogens recently, right? Didn't I say that these hydrogens were pushing electron density in? They inductively push. They're not electronegative, right? They're pushing electron density in. So what's that mean? That means then that the dipole moment of that molecule actually is pointing the exact opposite direction. So why does the molecule on the left have a larger dipole moment than the one on the right? It's not necessarily which way the dipole's pushing, it's what's creating the dipole. On the left-hand side, we have a carbon-OH bond. That's going to be a far more polarized bond than a carbon-carbon bond, even though we're still getting a polar molecule there because it's not the same as the hydrogen that's directly across. Any questions with that? Yeah.
Do the lower dipole moments make the length of the bond smaller? Since they're less polar?
I love that. I love that question. I think I'm going to answer it this way. The overall molecular dipole does not impact the. Ooh, boy, that's a tough one. I don't like to put like huge rules down. I'm going to go with the overall molecular dipole does not impact individual bond lengths. It's just the polarity of those bonds that does that. Okay. Did that make sense? Okay. Okay, draw the three-dimensional drawing of ethylene, which is that molecule right there. Predict whether it has a dipole moment. Okay. Let's see, so ethylene. I even see the bonding structure there. So I have C double bond C. I see I have H's connected to it. The hybridization of those carbon atoms are
SP2.
sp2, which means this whole thing's flat, right? So this is sp2 hybridized, which means the molecule is actually rendered exactly how it should be rendered, meaning all the hydrogens and carbons should be in the plane of the board and should be maintaining 120 degree bond angles. So is this molecule polar?
No.
No, and the reason why, great. And the reason why is because there's no bias here. There's no region of this molecule where electron densities can be skewed away from the other side. Everything's pointed directly across from each other. If I was to create something that looked like this, so this is of course mu is equal to 0. If I was to just make this simple substitution, is that molecule polar? Yes. And most likely I would predict that the dipole moment would be something like that. Yeah.
So would that be polar because it's it's sp3 and not?
No, so no, it still has the overall, that's a good question. So this here, from a molecular point of view, there is no region of space where I don't have something equally and opposite of the exact same character, meaning that there's no bias here in electronegativity. However, in this one here, when I now look in this direction in particular, this hydrogen can't counterbalance what that methyl's doing, and as a result, it's pushing electron density in and it can't counterbalance that.
Alright, so it's supposed to be like mirror image for both sides. It's kind of supposed to be the same.
Yes.
If it's okay.
Yeah. Yes. Yep.
Is that CH3 is changed with an oxygen equal that here?
Exactly, yeah. So if I was to make an enol, which you guys will, with me, thankfully. That'd be a horribly biased molecule. Yeah, this is like a month and a half from now. But I just want to say, I mean, that question there, this would be, you're entirely right. The dipole moment would be something like that. Yeah.
Could you explain again why the first one does not have a dipole moment?
Got it. Yeah, and I wish I brought a modeling kit with me to show you. So what I'm really describing here is one, because this molecule is flat, meaning it has sp2 hybridization, and every one of these hydrogens and carbons are in the same plane. When I'm looking at this overall molecular dipole, I'm looking for a region in this structure where the electrons are not being either delivered or removed at the same level. If this was twisted, it would be polar, but in this case here, everything's in the same plane, which means there's no bias in how these atoms are arranged. And as a result, because they can cancel each other, there's no dipole.
And it's non-polar.
It's non-polar, yeah. This one here would be, I'm gonna make up a number, 1.5. And if it's right, that'd be amazing. Okay.
So at this point in the class, we could rotate that molecule and change it to wedges and dashes and it would still be okay?
Without a doubt. Yeah, I love it. We can't do this enough right now because chirality, oh, it's coming. So if I took that molecule that's flat like this and I rotated it by 90 degrees and then drew this back to me, that's also, even though it's a little artsy, it's also describing that flat structure, except now that molecule is exactly perpendicular to where it was. Yes? Who answered that? Who asked that question? Yeah, okay. Yeah.
So are you saying if something has, like everything has sp2 hybridization, it's not polar?
No. sp3 molecules can be polar. sp molecules can be polar. So let's do that. So if I was to give you this structure here, would you predict that molecule to be polar or non-polar? Non-polar, right? Now what if I did something like this? Would that molecule be polar or non-polar? Be polar, right? We see a bias. We see a bias in a region, even though this is a linear structure, that methyl is pushing in against the hydrogen that can't counterbalance that and leaves an overall molecular dipole. Okay, other questions? I saw hands kind of raising. Okay. So, this then leads to formal charges. We've already been kind of kicking it around already, but we'll go through it very specifically because that's at the early stages of chapter 2. So now that we can draw these beautiful Lewis dot structures, we can now render anything into 3 dimensions. How do we figure out if we have formal charges or not? I would not suggest using this formula. It's a ridiculous thing to remember. I like the one that's a little bit more natural, which is, I'm gonna give you a periodic table, which means you'll never get this wrong as long as you have a periodic table for the time being. If you memorize where all the atoms are, then that's the next level, but you don't have to do that for this one. So in this case here, at times it is necessary to have structures with formal charges on individual atoms. So in other words, whoops. Nope, I didn't oops it, that's right. So we have here methylamine, or methylamine, well, no, it'd be methylamine. In this case here, what do we have? I think I have all the appropriate Lewis dot, all the electrons there. I have octets, 2, 4, 6, 8, around everything. And now if I want to count formal charges, I just look at the periodic table. So I'm just worried about nitrogen at this point. Nitrogen has 5 valence electrons. In this case here, each bond counts as 1 because it's a sharing of 2 electrons, which means that this is 1, 2, 3, 4, 5. Nitrogen has 5 valence electrons in this structure. Nitrogen up there has 5 valence electrons, which means this would be neutral. Okay. Complicit head shaking, that's what I'm looking for, right? That should not be mind-blowing. So if I go like this, that's an appropriate Lewis dot structure for that. What do? I go through and I count the number of valence electrons. Now that's what this formula is doing. The number of valence electrons in the free atom. That's counting the number of valence electrons off the periodic table. The number of valence electrons in the bottom, in the bonded atom, which ultimately is summarized by the number of bonding electrons divided by 2. So what is that divided by 2 thing? That's me counting each one of these bonds as 1. Right? We don't need that formula. We can just do it right off the structure. So in this case here, this would be 1, 2, 3, 4. Nitrogen has 4 valence electrons around it. Off the periodic table, it wants to have 5 to be neutral, which means we're missing 1 electron, which means it has a positive charge. Okay. So how about dimethyl sulfoxide? So let's take this a little bit farther. So that is the formula for dimethyl sulfoxide. So let's see. So what's the first thing we should do? Well, we'll count valence electrons. So we have sulfur. That's going to have 6 valence electrons. I only have 1 of them. I have an oxygen that has 6 valence electrons. I only have 1 of them. I have carbon. I have 2 times 4 valence electrons, which is 8 valence electrons. And then, of course, I have hydrogen, which I have 6 of them. So I have 6 times 1, so 6 valence electrons. 26. Now, why am I doing that? I'm going to make sure this structure looks right. Right? I have to have every one of these electrons counted for in either a bond or a lone pair. So what's the next thing I'm going to do? Well, I see the core structure bonding in that formula. So don't get thrown off by this. Sometimes I'll write you condensed formulas where you have to put things together. In other cases where I draw a structure like that, I'm describing where those methyls are. The methyls are attached to the sulfur. They're not attached to the oxygen. So what's that saying to you? So the way that that's drawn, that means I have a sulfur that has 2 methyls bonded to it. And an oxygen bonded to that. So this is where the 26 electrons come in, and this is where I'm going to fill them in. I'm going to say, at this point, I want to make sure I have octets around everything. So let's see, that would give me an octet up there. I see I'm 2 electrons short down here. I'm going to put an octet right, I'm going to put a lone pair there. Right, I'm just filling up, I'm just using the octet rule to see if that accounts for now the valence electrons that I need, which is 26. So starting over here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That's fine, right? Now I'm missing my formal charges. So what would be the formal charge of this oxygen based on the electron configuration I gave it? -1, right? So 2, 4, 6, 7. Oxygen wants 6 to be neutral, it has one more than it, be negative. So this sulfur had better be positive because this molecule is not charged. So let's see, so 1, 2, 3, 4, 5. So that would be +1. The overall molecule, of course, is neutral because I have negative and positive charges in the same molecule, which gives it its sulfoxide name. So this would be the Lewis dot structure of dimethyl sulfoxide. This is also showing the formal charges that are present on that molecule.
Should oxygen be in the middle as well, and then sulfur where oxygen is?
Ooh, I love the out of the box thing. Let's see if we can do that. I'm into it. I'm into it. So let's say dimethyl sulfoxide was this guy, or gal, or female. So let's see, so that would be there, then we're gonna put a sulfur there. Okay. There's literally nothing connected to sulfur, which means that this is the thing that would be like this.
Should the same, but shouldn't we have sulfur in the middle to just expand?
Well, let's see. So we have 2, 4, 6, 8. So it's not an expanded octet.
Well, what I'm saying is like it will give the same answer because they're both technically have the same valence electron. They have to have 6 on both, but shouldn't we like correct like drawing have the S in the middle because it can expand if you do?
I'm trying to think of the right way to answer it. I'm going to go with, you're correct. So in other words, the reason why sulfur is in the middle of this, the reason why dimethyl sulfoxide is such a great solvent is because sulfur has such flexibility in the number of electrons that can be there, and oxygen doesn't have that. I agree with that. But for the current exercise, I'm driving at something with this. So, even though it's incorrect, I'm driving at something. So we'll get there, and then I'm going to make a point. Okay. So in this case here, we have so we have octets around everything, and in this case here, that would be a negative, and that would be a positive. And of course, this isn't the structure of dimethyl sulfoxide, but this is something that maybe if you drew to me, I would say, okay, interesting, path to take. Now, why can this not be the structure of what we're looking at? Exactly, right? So when it comes right down to it, when you look at the electronegativity table, sulfur is less electronegative, right? As you get farther away from fluorine, it becomes less electronegative, which means it is less willing to hold a negative charge. So in this case here, me putting a positive charge on oxygen is the ultimate, that would tell me that is the least stable orientation I could ever have of that molecule, because I'm putting positive charge on the species that would never want to be positively charged. Right? It wants to keep electrons. It doesn't want to give them up. Yeah.
So obviously this form is very unlikely, but could we possibly be asked a question like to show all resonance forms even if they're unlikely? Does that make sense?
I
Or
do.
no?
I do.
Okay.
And I'm liberal to a point on that subject, meaning that you guys are just learning how to draw things. If you draw me something so wild that I go, oh my God, that could never exist, I'll still take the ride with you as long as you're obeying all the rules. Right? So if I had the option between these two structures, I would always want to put the negative charge here. But if you gave me this one, I wouldn't be, well, of course, there's a negative positive. I wouldn't be, it wouldn't be right, but it wouldn't be a 0, right? It would show that you actually knew what you were doing. So I'm into that. Yeah.
So if we were looking at the CH3 groups at the bottom, and we wanted to put those into like dashes and wedges, each one of those would have one dashed one and one wedged one, because one H and one S would have to be in the plane.
Yeah, that's exactly right. So I'm gonna leave this, so in your notes, I would just love like that in them. That is not dimethyl sulfoxide, right? This one here is. The other reason why is because of how that structure was written to you, meaning when I wrote CH3,2SO, I'm describing the bonding in that structure. I'm saying the methyls are associated with sulfur, not with oxygen. And to your point, Claire, right? That was your name? Claire. And so, yes, so if I was to draw this molecule, this would be the hydrogen, this hydrogen would be in the plane, and of course then I would have hydrogen coming in and out of the plane. Same thing here, H, and then we have our oxygen there. And this would be a positive, this would be a negative, and of course, what would be the bond angle between here and here? Yeah, I heard a mixture. Give it to me again.
No, the 109 because there's the.
109.
Yeah.
Why is it 109?
Because there's the low.
Yes, we got 4 electron containing things around sulfur, which means it has to adopt a tetrahedron, which means it has to be about 109. Okay. Yeah? Alright. I thought this was a beautiful picture out of McMurray about the electron density of dimethyl sulfoxide. It even shows you in the electrostatic map the fact that the oxygen has this high amount of negative charge, and there's actually very little negative charge on that sulfur. That ends up resulting in a pyramidal structure for this molecule because sp3 hybridized. Okay. You do not want to memorize tables like this, right? You want to be a lot more flexible in your life, especially when you go and take MCATs later on. This stuff is going to be a part of that. So what we're talking about here, looking at structures and counting formal charges, is far more flexible and a path to success in this course than taking that table and memorizing every one of the possible options of valence electrons around things. Yeah?
I guess. Then, correct, you don't want to draw like also
It doesn't have to expand the octet, right? Because I only have one extra pair of electrons there. But if I created a charged sulfur species, then yeah, that would be the place I would expand it. Go ahead.
I mean, so would it be better if you're supposed to be two electrons,
Well, I think the other thing, I think the other thing that you're knocking on the door of, William, is this. So another way in which dimethyl sulfoxide can be written is like that. Now, this doesn't describe the bonding as accurately as this. The reason why it's called sulfoxide is because literally there's an oxide on it with reference to its bonded structure. This one here, you can see how there might be an issue, right? It's supposed to be sp3 hybridized. It has that structure here. But if you go ahead and count the electrons, you would find that this actually is a possible resonance contributor of that. And that those bonds are a little bit flatter. But I just sort of put this up as an example. Hopefully that touches on what you're describing. Yeah, okay. Okay. Make sure we're doing okay time-wise? Yeah, we're doing okay. Last thing. So, we have methyl phosphate dianion right here. We're going to walk on through and come up with where those negative charges are actually placed on that molecule. Okay, so what do we got? We got methyl phosphate. So there, H, O, P, O, O, O. This is described as an overall dianion, which means I have 2 different negative charges somewhere on that molecule. So really what you're being asked is what are the formal charges on all these oxygens? On this oxygen here, 1, 2, 3, 4, 5, 6, that'd be neutral. How about that oxygen there? What would be the formal charge on this one? Neutral, right? 1, 2, 3, 4, 5, 6. How about that oxygen there? right? Negative 1. 1, 2, 3, 4, 5, 6, 7. It has one more electron than the neutral 6, which means this would have a negative charge there. Same thing would go there. Okay. Which is what we just did. We just instead of us, I just dropped doing the math example, and I just used the more flexible way in which you have a structure. How do you calculate formal charges? Look at how many valence electrons there are. Look at how many valence electrons are around the atom. If it's greater than it, it's negative. If it's less than that number off the periodic table, it's positive. And we are knocking on the door of resonance structures, and I think that subject's so enjoyable, we're gonna wait till Thursday to do it. So, any questions? Yeah, go ahead.
Yes, on that one, no, the sulfur has anything to do it or not?
What was that?
The sulfur has a.
No, it doesn't have a negative on it. I've used it as bonding, but this resonance contributor is not the actual structure of that molecule that sulfoxide was. Has 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh, you're right.